Have you ever looked at an engine, kind of like this one on the two-wheel tractor, and just wondered, what is with that giant, heavy wheel on the side? It almost looks like it's too big, right? Well, it turns out it's there for a really, really important reason. It solves a huge problem right at the heart of how these engines actually work. So today, we're going to dive deep into the flywheel. It's this surprisingly simple part that takes the incredibly violent, jerky power of an engine and, tames it, turning it into the smooth, steady force that basically moves our entire world. So here's what we're going to cover. First, we'll look at the engine's big problem, its uneven pulse. Then we'll actually chart it out so you can see it. After that, we'll get into the physics of why it happens, introduce our hero, the flywheel, and then, finally, see how it all comes together for a nice, smooth ride. Okay, let's jump right in. First, we need to get a real handle on the core problem that needs solving inside, well, pretty much every piston engine out there. So the main issue is this. An engine doesn't give you a nice, smooth, continuous push. Not at all. It's more like a series of really short, really powerful kicks, one after another. And that jerky delivery is the exact opposite of what you want for a smooth ride. Everything starts with the intake stroke. You see, the piston moves down, which creates a vacuum, and that pulls a mix of fuel and air right into the cylinder. Just think of it like the engine taking a big old breath. Next up is compression. The piston shoots back up and squeezes that fuel and air mixture into a super tiny space. Now, this part's really important. This step doesn't create any power. In fact, the engine has to use energy just to make it happen. And then, boom, the main event. The spark plug ignites the mixture, there's a huge explosion, and it just slams the piston down. This, right here, is the only moment in the entire four-stroke cycle where the engine actually makes any useful power.
And finally, we have the exhaust stroke. The piston moves up one last time, and its job is just to push all those used up burnt gases out of the way to make room for the next cycle to start all over again.
So here's the key takeaway from all that. For a typical four-stroke engine, you only get one power-producing kick for every 2 full turns of the crankshaft. That's just one moment of go for 3 other moments of basically coasting. And this creates a huge mismatch, right? The engine is supplying power in these wild, pulsing bursts, but the vehicle, and let's be honest, you, the driver, you want constant, smooth power to move down the road. So what does this actually look like? Well, if we put it on a graph, this pulsing nature of the engine becomes incredibly clear. It really puts things into perspective. Before we look at the chart, we need to know what we're measuring. It's something called turning moment. And don't let the fancy name fool you, it's really just the twisting force, or torque, that the engine is creating at any given split second. And here it is. This is a turning moment diagram, and it just perfectly shows the problem we're talking about. The line along the bottom is the crankshaft spinning around, and the up and down line is the torque. As you can see, it is anything but a straight line. It's all over the place. Now check out that one enormous peak right in the middle. That's our power stroke, the working stroke. All the useful energy for the whole cycle is generated right there, in that one brief, powerful surge. It's a huge surplus of energy. But then, look at the other side of the coin. See that big dip during the compression stroke? The torque actually goes negative. The engine isn't making power at all. It's literally borrowing energy from its own momentum just to keep going. So to make this all work, engineers draw this straight line across the middle. It's called the mean resisting torque. And you can just think of it as the steady, average power the car needs to run. The whole goal of our system is to somehow shave off that massive energy peak and use it to fill in those deep valleys, trying to get everything as close to that average line as possible. So what's actually causing these insane swings in torque? Where does that crazy shape come from? Well, the answer is in the physics, specifically 2 powerful forces that are constantly fighting each other inside the engine. So that turning moment is mostly dictated by 2 big things. First, the obvious one, the incredible gas pressure from the explosion pushing the piston down. But there's a second, sneakier force, inertia. Think about it. That piston and connecting rod have to slam to a stop and reverse direction constantly. That creates its own set of powerful forces. Now, you do not need to memorize this formula, but it shows us exactly how those forces work together. The turning moment, T, is based on both the force from the explosion, Fp, and that inertia force from the moving parts, Q. Both of them are what create that super bumpy curve we just saw. In this, finally, brings us to the just beautifully simple and elegant solution to this whole roller coaster of a problem, the flywheel. So, what is it exactly? Well, the simplest way to think about a flywheel is as a mechanical battery. Yeah, it's just a heavy spinning wheel that's designed to do one thing really well: store and release rotational energy. And here's the genius of how it works. During that one massive power stroke, when the engine is making way more power than it needs, the flywheel soaks up all that extra energy, and it speeds up just a tiny bit. Then, for the other three strokes, when the engine is just coasting or even using energy, the flywheel releases that stored power, slowing down just a little, but carrying the whole system through smoothly. It stores all this energy as kinetic energy, and this little formula tells us how. The amount of energy it can hold depends on its inertia, which is basically just its weight and shape, and the square of how fast it's spinning. So a heavy, fast-spinning wheel can store a ton of energy. Okay, so where does the flywheel fit into the grand scheme of things in modern engines? Is it the only trick that engineers have up their sleeve to make things run smoothly? Now, some of you are probably thinking, hey, what about cars with 4, 6, or even 8 cylinders? And you are absolutely right. Adding more cylinders helps a ton. It lets you overlap the power strokes, so the whole delivery is way less peaky. But it's almost impossible to get it perfectly smooth with cylinders alone. There are always little bumps left over. And that is why every single piston engine, from that humble little tractor we started with, all the way to the most advanced engine in a brand new car, still has a flywheel. It is the final, essential piece of the puzzle that smooths out those last little jitters and gives us that steady power we expect. It's an incredible idea when you really stop and think about it. This principle of a simple wheel acting as an energy bank is used everywhere, from giant factory machines to literally steering satellites in space. It really makes you wonder, doesn't it? What's the next huge, complicated problem we could solve with an equally simple idea of just saving a little energy for later?